Hi everybody. In this short video I'm going to talk about the Agile development process, in particular about automated regression testing and how this applies to Project 1A. So this course, as you've noticed by now, is not so much about the process but more about the structure and the architecture of the software we're producing. Now, there is a relationship between the two in the sense that when you look at the way an organization develops software, that organization has a structure, and the process, the development process, is about the interactions within the organizational structure. But we're not studying this very deeply or explicitly in this course. There are other courses where this happens, especially the software engineering courses, undergraduate and graduate. So here we're primarily focusing on the structure of the software that we're building. And this also has to do with this set of requirements topics in the following sense. Okay, the main requirement is, of course, the set of functional requirements, which describes what a piece of software does, how it behaves observably. Now, when we say this is usually not enough on its own, well, this depends. So if you're talking about a piece of software where you're interested only in running it once and then getting an answer and then throwing that piece of software away or not paying further attention to it, then that piece of software in itself would not be considered an asset. It doesn't have value in itself. The only value is that one answer it produced when you ran it. So it's kind of like the program as a way to capture the equivalent of, say, key presses on a calculator. So that type of software occurs in situations. Sometimes this is the case for, let's say, short shell scripts that you write just to get a one-time task done. Also in some situations where you're solving a small scientific problem or so. But usually software is an asset in itself, meaning it has value beyond running it just once or twice. It's something that you want to be good enough that not only can you use it effectively in terms of the functional requirements, but you can also respond to changes in the functional requirements, or you can even, before you do that, even in the shorter term, you can make sure that it actually satisfies the functional requirements. So hence, the non-functional requirements. The non-functional requirements describe the internal qualities of the piece of software, which in this handout we're calling F, in analogy to the piece of software performing a function on an input X and producing a result Y. Okay, so the non-functional requirements state the characteristics that F should have in addition to the functional requirements. And the most important one of these is actually testability, because this allows testing whether the functional requirements are met in the first place. That's precisely why so much attention is being paid, even in a lightweight development process, to testing, and testability. And then, as Uncle Bob tells us in the Agile PPP book on pages 36 to 38, when you follow, as you develop, the goal of making your software testable, then good architecture often happens as a side effect on its own, what he calls serendipitous architecture. So, of course, we'll come back to testing. We'll elaborate a little more on this shortly, and this is the part that's in preparation for Project 1A as well. Other important non-functional requirements are performance, scalability, so that can refer to performance for increasingly large data sets. So this is tied to the asymptotic order of complexity. For example, big O in terms of input size n. And reliability, referring to the rate at which a piece of software will actually function. So, for example, if the software F produces the correct result in, for example, 90% of the times that you run it, then that would be 90% reliability. That is different from not meeting the functional requirements. This is actually tied to the question whether you prefer a piece of software to give you the wrong answer or to crash instead of giving you an answer. And I will leave that up as an exercise. So suppose the piece of software is supposed to help you make a billion-dollar decision. Which do you prefer? Do you prefer, let's say, if there's something wrong with the software, do you prefer it to crash visibly, noticeably, or do you prefer it to run and give you a result that you cannot trust? Okay, then maintainability allows you to evolve your code in response, for example, to changing requirements. Then non-functional requirements can be classified as static versus dynamic. Okay, so static ones are the ones that you can observe by looking at the code, and dynamic ones are the ones that you can observe by running the code and, for example, measuring the running time or looking how often it crashes. So that's another exercise for you, which of the ones listed here are static and which ones are dynamic. Okay, so now that we have this requirements terminology, and of course, again, in a software engineering course, you would go into a lot more depth about requirements. Here we just want to have a basic understanding so that we can talk meaningfully and understand why we structure our software in certain ways. So coming back to week 3, this basic Agile development process. This is how Martin Fowler describes the key elements of an effective development process in the 3rd edition of the UML Distilled book. And Martin Fowler he's the chief scientist of the global but Chicago-based consulting company ThoughtWorks. And you should at least be familiar with the ThoughtWorks technology radar. So here's an invitation to Google that and take a look. And a consulting company like ThoughtWorks is involved in a lot of projects and sees what works and what doesn't work over time, and is therefore in the position to make this kind of statement. So according to their in-depth experience with actual client projects, these are the key elements that work. And one of them is automated regression testing. The other one is refactoring, which we'll look at separately. And the third one is continuous integration and possibly delivery. And well, briefly, so refactoring means you change the quality of the code without changing its functionality, so very abstractly speaking. And this really means, for example, if you notice what is called a code smell, such as code duplication, let's say the same piece of code more than once, where you could just refactor that by expressing that functionality as a method and then invoking that method from the two places where the code was duplicated before. That would be a good example, a very common example of a code smell, such as duplication, something that just doesn't look or feel right in the code, and a refactoring that eliminates the smell. And Martin Fowler also has a book on refactoring, but it originally comes from Ralph Johnson's research group from Urbana-Champaign, who is talking next Thursday at actually the ThoughtWorks offices. So that's the Go To Night Chicago. And continuous integration in its technical form means, well, you set things up in such a way that when someone makes a change to the code base, then and commits and pushes that change into the repository, that it automatically triggers a build of the whole project, and including the automated regression testing, so that you can immediately see whether that particular change caused other things to break. And this is actually a good time for the quick joke about, it's one of those light bulb jokes. And this one is, how many C++ programmers does it take to change a light bulb? Anybody? Well, I guess I'm just by myself here recording. So the answer is it takes only one, but after he's done, the refrigerator and the sink don't work anymore. Okay, so it's to illustrate that when you have complex code and you're thinking you're making a localized change, the change might have effects that you cannot predict. And continuous integration is supposed to dramatically reduce the time it takes to discover such an effect, such an unwanted effect. So normally, again, so someone commits a change and it causes a build and a regression test to happen. And if something goes wrong, then certain people maybe get notified by email or by a text message or so they can respond immediately and check who might have caused this build to break, and then they can get in touch immediately with that developer and get them to maybe fix it or revert to the previous code or the previous version of the code or things like that. So it's supposed to improve things considerably from, let's say, weekly build or even irregular build and regression testing. And when you add continuous delivery to continuous integration, it's like taking this idea even further in such a way that whenever a change is made, and if that change passes the regression testing, that it gets pushed out directly to the users. So that's, of course, a little harder with a shrink wrap piece of software on a CD, which is kind of the older style, but it's increasingly common with current modern delivery mechanisms such as browser-based applications, etc. So how does that then relate to or rely on automated regression tests? Well, the continuous integration includes automated regression testing as a very important step. And that's one of the various reasons that automated regression testing is so effective. Now, you might say, well, if I write a piece of software, well, I can kind of look at the code and convince myself that the code is correct as long as I'm using the right kinds of algorithms, etc. So this is somewhat true in very limited circumstances. So one, if you're working on your own, perhaps, and the software that you write is fairly simple, then this is partially true. But in real life, that is rarely the case. Neither of these things would be the case. So usually you work as part of a team, and the more complex your software, the larger your team might be. And real life software, as you're getting a little bit of a feel for in this course. So we have maybe small to medium size projects here, but you will see that they're sufficiently complex that you don't want to just do a kind of code review as the only way to convince yourself that that you did everything right. Whereas if you can test your software, you will have an additional mechanism for building confidence in the correctness of the software. And the thing is, it's very tedious to test software manually because you basically have to type in all the same stuff over and over. Let's say you make a small change, then you have to manually repeat a whole long sequence of interactions with a piece of software. And that's why, unless it's automated properly, it's not going to happen. It's extremely unlikely it's going to happen. So how do you make it happen? Well, you could say, ooh, and that's kind of the brilliant idea behind the X-unit approach, that paradigm is, well, why don't we figure out a way to make the tests pieces of code? And programmers love to code, so let them code the tests as well. And then they're going to like doing that, and then it's going to be automated, meaning you press a button or it gets triggered by the build or so, and then the test suite runs. And that's what makes this very effective. And the whole point is regression testing, meaning whenever you make a change, you run that regression test suite, and that allows you to make sure that whatever worked before still works after the change you just made. And that's enormously valuable. So these are the three key elements. The other thing I mentioned here was a repository, and of course you're already up to speed in terms of having set up a Bitbucket repository or multiple Bitbucket repositories. Why would you need a repository when you can do things like Dropbox, to cooperate across your own machines or even to share a code base with other teammates? Well, the thing is, Dropbox is good for shared storage or just even cloud-based storage that you're sharing just with yourself, so that's great. But it doesn't have things like versioning, where you can actually go backward and forward in the history of your development, or where you can have multiple branches. Let's say you have a main branch that is the current version of the software, then you might have a development branch that will reflect the new version that's still under development. And all of those things are not supported by, let's say, cloud-based storage. Okay, so in that sense, distributed version control systems such as Mercurial or Git go far beyond just cloud-based storage. They allow people to collaborate in very effective ways. So that's why in this course and in general in your career as software developers, I highly recommend using distributed version control systems such as Mercurial or Git, even when you're the only person working on the code, because that might change and you can collaborate very effectively with yourself in terms of going back and forth and just dealing with branches and simply having an opportunity to develop a skill or familiarity with that type of tool that's very highly valued in the professional world. Okay, very good. Then this other point I was going to make briefly, just because it's up, is there's also this key trade-off. To be agile, what you usually try to achieve, very broadly speaking, is avoiding unnecessary risk. And in conjunction with this, you usually avoid what's called BUFD, meaning big upfront design. That's considered to be a high risk. So therefore, usually the aim is in an agile development effort to produce an MVP, a minimal viable product, which is basically, let's say, a version of your software with the fewest features that is still meaningful. So that's considered a low risk approach where you're doing an MVP initially. Okay, now in the rest of this video, I will zoom into automated regression testing and take a look at how this applies to project 1A. Okay, so a lot of the concepts, can be seen in our echo test example. So the echo test example, if we look at the main section of the code, we have a main method here that simply creates a sequence of two echo objects, a simple echo and a double echo, and then says, well, for each of them, let's see what it echoes. Okay. And, we can, of course, run this by right-clicking into the editor window, and then we can run it, and it'll say, well, okay, the first one is the simple one that does a simple echo, and the double one does a double echo of the argument. That's kind of what we expect. This is simple enough. Okay. What is echo? Well, that's just a trait which is something in Scala that's similar to an interface in Java, or can also play the role of an abstract class in Java, in the sense that traits are not pure specifications like Java interfaces, but they can also have implementation code in addition to specifications. But if you have a pure trait like this, without any implementation that's equivalent to a Java interface. Okay, then we have, and you see how the main method basically creates the sequence of different implementations, and we should be able to, on the Mac, for example, Control-Shift-P, it should tell us what the type of an expression is, and this says it's a sequence. So sequence is kind of a list, a generalization of a list. So this says it's a sequence of echo element type. So it noticed that both of these have echo as the common trait that they implement. You can see that here. So simple echo extends echo, and double echo also extends echo. And I also showed something here where you can do an import, and when you have these multiple package statements in Scala broken up like this, then you can have kind of relative package paths. So the main, it'll try to find the type you're importing relative to some of these packages on this list of multiple package statements. Okay, so now we got those two. See, and here it just does this same thing without importing. Okay. You see one thing that's kind of related to what is required in Project 1A, which is a separation between the main app, which acts as a driver. It creates instances of the classes that provide the logical functionality and is responsible for, in this case, just output, but in 1A, input and output. Whereas the classes that implement the logical functionality should not have any input-output responsibility, just like these. So that's something that makes these classes that provide the functionality much more testable. That's right. So they can be tested automatically. If they had input-output responsibility, then one would have to either manually provide the input and review the output, or one would have to script that externally to automate it. And both of these are tedious. When instead we can simply do a proper separation of concerns between something like a main driver and other components that provide just functionality on data, on structured input data, producing structured output data. And when we have that separation, then we have a little bit of this, in a very simple form, this serendipitous architecture where making something testable also made it architecturally nicer, more modular, better separation of concerns, and then we can properly automate the tests. Okay, and now in JUnit and other similar XUnit frameworks, okay, we have several possible outcomes. So we can start by looking, because most of you are likely to be familiar with JUnit than these other more modern specs-based frameworks for behavior-driven design and other more modern test paradigms. But so what we have here is a class. That's how it works in JUnit. And any method that's annotated with this @test annotation, that's going to run automatically when you run this test class as a test class. So the JUnit test runner will automatically discover the fact that some of these methods are annotated. And then you have assertions. So normally you might have multiple statements to interact with the object you're testing. That's called a subject under test, or SUT. And so you interact with it, you make certain state changes to it or so, and then at the end you verify by means of an assertion whether the state has become what you expected it to become. So here, these are very simple stateless behaviors. So these echo implementations don't have mutable state. They don't have mutable instance variables. So we can just invoke the method on an argument and then verify that the result is what we're expecting. And these assert equals work like this. So the first argument is what you expect it to be, and the second argument is what you're testing. And so this says basically if you're invoking the echo method of the simple echo, you're expecting to get back what you supplied as an argument. So in both of these cases. And then double echo, that's of course part of the exercise. And then I just added these to illustrate another kind of possible outcome. And the outcomes are, well, the assertion can succeed, right? So then it passes or succeeds, and then it either doesn't get shown down below in the test console, or it shows as, let's say, a green check mark, typically. And when you have a failed assertion, it usually gives you, let's say, a yellow X or something like that, or yellow exclamation mark. Well, then there's another kind of error situation other than just the assertion succeeding or failing. So that would be, and let's fix this method name. Okay, that would be when something goes wrong on the way to the point where you're testing the assertion. And in fact, we're going to write this more like this. So val result. So see, I like to code live. You will notice that as you take additional courses with me. So let's do this here also. We'll propagate this. This is an example of repeated code, of course, but here we're just kind of playing around with the testing, so it's not that big a deal. Okay. All right, so here we go. So what do we see here? Well, first of all, let's run this so we have more concreteness. Normally what you do again when something is recognized properly as a test suite, in your IDE you can right click, pull up the context sensitive or context menu, and then you can say run the thing you're clicking on. And then what do we see here? So let's look at the lower left corner. We see a yellow exclamation mark, and you can usually click here, and it'll give you the specific error message for the failed test. And here it says, okay, there's a comparison failure between expected and actual. Then you can click here to see the difference. It'll show you nicely and visually in the IDE. That's all the IDE support. But when you see expected and actual, it's because an assertion where you're comparing an expected value with an actual value has failed. And that's the case here, and then that's also the case here, except you cannot really see it, except when you pull it up, you sort of see that one has, one is a little different from the other. And again, that's your job that was your job, of course, for Project 0C. Okay, now there's another test listed here that we'll look at in a second. But what you notice is that there aren't any green ones because the green ones are actually all collapsed, because the assumption is, well, why would you want to look at all the ones that pass? Because presumably the ones that passed, there should be a lot more that passed, and you don't want to clutter your view with that. But you could, in principle, maybe expand this. Let's see. No, that's just for sorting. Okay, here. So now this is if you looked at the whole thing, and then this is. Oh, I see. So this is hide past, this button here. Okay. So here, that's the default setting. Anyway, now, what about this one? And why is this a red exclamation mark? Well, here we see, oh, so there's an index out of bounds exception. And, well, let's see where this happened. So here we can usually click, and it'll take us right there. And what do we see here? Well, we created this list with an echo instance, and we tried to access the item with index 1 in that list. But this list has only one item, and in Scala, just like in Java or in C, these things are numbered starting at 0. So there is no item with index 1, and therefore we get this index out of bounds exception. Okay, and that means we don't even get to the assertion. And instead, in fact, we should probably have written this. Let me fix that as well. We'll use this, and then because that's not a JUnit assertion, we really want to use a JUnit assertion like this, to make it consistent with everything else. Okay, so that's good. And still, the behavior won't change. Okay, so here's the index out of bounds exception, meaning something blew up here, as we can again show by clicking on the corresponding line in the stack trace. And this is because we tried to use an index for which there wasn't an item, and we didn't even get to this line where we would have tested the assertion. Now, that's always a possibility if you're doing complicated stuff and something goes wrong before. But through the stack trace here in the bottom right view, you get a lot of information that usually helps you pinpoint the problem. Now, what happens here? So in this last method here, why doesn't this blow up? Well, here what we're expressing, let's take a look. What we're expressing here is we're saying, okay, this is our list of echo instances with just a single echo instance in it. And then we'll say, okay, let's obtain the result. And if, in fact, this we should probably eliminate, because we really want to say, well, if we get past this line, that's a fail, because we should have gotten an index out of bounds exception by now. But because we don't get this fail, the test passes. And why don't we get the fail? Well, because the index out of bounds exception occurs here, but we're catching it here in this try catch block. So in other words, from here, when the exception occurs, we jump to this part here, and then there's basically an empty expression as the result. If this succeeded, so let's say if we put 2 simple echoes in here, and then rerun the test, then you will see a fail with this error message. And here you go. So test simple also using list. It says here should have gotten an index out of bound exception by now. So we'll get rid of this. And again, because in this case there was no exception, so we went straight to this fail. That's what happened. Okay, so what did we see here? Well, we saw these three possible outcomes for each test method. The test passes, which is usually hidden from the view in the IDE, or the test fails in terms of an assertion failing, or we don't even get to the point where we're testing an assertion. So those are the three outcomes. Okay, so you can then use these techniques in designing your test suite. Also, in designing a test suite, it's very helpful to test your boundary cases, such as empty input or whatever, or certain other boundaries that there might be, and then to test a variety of possible input scenarios. Now, in the echo test, there are various test classes. And of course, the echo JUnit is probably the most familiar one. The other one I wanted to show is echo test, which is essentially the same thing, but using the Scala test framework, which is a very flexible test framework that's really designed for Scala. So this fun suite flavor, and if you look at the scalatest.org site, you can see this documentation with a number of different flavors that appeal to developers coming from different kinds of cultures. So one thing is the XUnit paradigm, where you do assertion-based testing. Another one is called behavior-driven development, where you're usually expressing the behaviors more verbally and then structuring your test suite accordingly. So you'll see some examples of that there. And we'll also see some examples of that in some upcoming examples, in some upcoming code examples for this course. So here, these are the equivalent tests that you saw in the echo JUnit. And here, same idea. If we run this, well, here we're running just a single one. Oh, okay, it ran the whole thing. Okay, good. So here, what you're losing is this distinction that you have in JUnit between a failed assertion and an error. So all of these are just treated the same way. So there's no distinction between yellow and red exclamation mark. But other than that, it's the same idea. So the interesting thing is now there's better, more concise support for expressing that you're expecting an exception. So here again, what we're expressing in this test is we're saying, well, we got this list of a single echo instance, and when we're accessing item 1 in that singleton list, we expect an index out of bounds exception, and we intercept it. And that's why this test succeeds, whereas the other one here, where we're trying to do an assertion, fails. So I'll make this consistent with the other ones. Okay, so here we go. Let's rerun this. And as you saw, you can run these individual tests. Let's see if it's possible to run all tests here. And here's what happened. So it ran all tests in the sense of, let's see, in the sense of JUnit tests. So it discovered those that are JUnit tests, and I could have, in the previous one, run the Scala tests in this package. And let's see, so that is not possible anymore because we just made that choice. So now these others we'd have to run explicitly. Okay, so as you see, FunSuite is similar to JUnit, but you have this additional support. And in Scala tests, there are also things such as matchers, which are basically a domain-specific language that allows you to express expectations in a more readable way than assertions. So it reads more like a proper sentence in a human language. All right, now what about this spec and check stuff? Well, one of the design goals of testing is, of course, to be fairly exhaustive. And in many cases, you can actually express a very general property that you want to test, really. So if you look at echo check, you really want to be able to say, well, the simple echo behavior always echoes its argument, no matter what that argument is. And that's basically what happens here. So this is universal quantification, like a for all. It's like saying for all A, simple echo A returns A. And here, same thing with a for all quantifier. So for all A, we expect double echo of A to return A plus a space plus A. So this is so-called properties-based checking, originally based on the Haskell test framework quick check. So this is very cool and very powerful. And you might wonder, how does this work? Well, let's run it and see if we see any hints in the output. Okay. So let's make some room here. Okay. And let's show everything. So simple echo should echo its argument. Yeah, we can't see the output, but let's run it here. So let's go to echo test and then say SBT test. So we can see the output of the echo check test. Okay, so this is the part I wanted to show where it says simple echo okay passed 100 tests, and then double echo falsified after 0 passed tests. So it needed to try only one argument, such as the empty string, and it failed. Now the simple echo passed 100 tests. This suggests that it ran actually 100. It ran this for 100 different values of A. So those have to be generated somehow. And for common argument types, such as string or int, it knows how to generate a sequence of values for testing. So it'll do that automatically, and this is very powerful. If you have a more complex user-defined type, you will also have to supply a generator that goes along with your type. So it's still possible to use this approach. Okay. So then the echo spec is using Scala check instead of Scala test. Using Scala check directly, but otherwise it's equivalent. And one more thing I wanted to show, so you could actually, I think it goes like this, test only, and then you need, of course, this, and then echo JUnit. So in this way you can run, instead of running the entire test suite, you can run just a specific one. See, so it ran only this one JUnit based suite. Okay. So this pretty much concludes what I was planning to say about testing as an initial tutorial, a basic initial tutorial. Then later, as we get into some Android development, we'll also go into some more advanced testing techniques, such as mock objects that are basically fake objects that are connected to your subject under test as the dependencies of the subject under test in a more complex piece of software. And when you interact with the SUT, the SUT will interact with its dependencies, and when you mock those, then you can control more precisely how they behave, and then you can verify, for example, whether the SUT interacted with its dependency in the expected way. So anyway, this is just a very brief description of that, and we'll look at it in more detail. The other question that comes up, and it's actually a really good one, is how do I know that my tests are correct? Am I testing the right kind of stuff? And that is an issue, of course, in general. But one of the main ways to deal with that is to make sure that your tests are always very simple, usually very straight line stuff, or when it's these kinds of properties, one would have to take considerable care in verifying them. And again, that's why you might also try your tests using a fake implementation of the subject under test that behaves in a known expected way. Okay. All right. So now there was one more thing I was hoping to say about the Agile development process that I just remembered. So we just saw automated regression testing in very simple, basic ways. We briefly discussed refactoring, so we'll have some. I think we should be ready to listen to the software engineering radio episode on refactoring. So you could listen to this on the bus or in the car or wherever. These are audio podcasts. You can subscribe to them through iTunes or download them or whatever. And the other thing I wanted to say something about briefly again is continuous integration. There is also, in my opinion, a very, very lightweight way of, or mindset, a way of thinking about or of achieving something like continuous integration ultra light. When you follow the old recommendation for the development process, always to make sure you have a running system. So it's even tied to the minimal viable product idea. So initially, you have a running application even though it doesn't do anything. And then you very incrementally add functionality. So that's kind of continuous integration minus the tool support, the fancy tool support behind it that you usually have with a continuous integration machine set up, a dedicated machine where the build happens, etc. with the right kind of tooling. So if you just say, well, I always have a running system from development day one, and I always add just very minimally, you already have some of the benefits that you have in conjunction with continuous integration and delivery. Okay, so as long as then after every change you actually make sure that you try out the system and actually look at your regression tests. So very good. So let's now take a quick look at project 1A. Okay. Again, I made a few corrections and clarifications here. So again, I'm hoping that these structural requirements for testing make a lot more sense now that we've looked at echo tests a little more closely. Okay. And then this part, so I added a sample for loop that basically allows you to iterate over the input words without having to become an expert in Scala I/O. And then everything else should be quite simple, and it shouldn't take you a lot of time to finish this up. Maybe a couple of hours. It's certainly not much more involved than the echo test example. And again, to test the thing end to end, meaning functional tests at the observable level, you'll probably want to create a few input files, and that way you can rerun the tests at that level, in addition to having your unit tests of the components that provide the actual logical functionality. And to make that possible, again, you need only use this approach to read the standard input. So you want to always read from standard input. That allows you to redirect the input from a file or just type the input on the console without changing your code. That's the beauty. That decision where the input comes from, whether it's from the console input or from an existing file, that decision is made outside of your code at the operating system shell level. So I always recommend doing this, and most Unix shell utilities work exactly like that, and that makes them so nicely composable. Okay. Anyway, this is it for now, and I'll be in touch soon with more homework and more videos. All right, take care. See you soon during drop-in hours or online.